Assalamualaikum warahmatullahi wabarakatuh.
Waalaikumsalam warahmatullahi wabarakatuh.
Very good morning, my student. Today we are talking about heteroskedasticity. I'm sorry I'm in the remote area, so a little bit noisy here because I have an event. Now we are talking about heteroskedasticity, the classical linear regression model. Okay, in the assumptions of classical linear regression model, it is assumed that the variance of the residuals is constant from the first observations until the end of observations. Okay. Now today we are talking about heteroskedasticity. That means the variance is not constant of the observations. Okay, we are dealing about 4 topics here. What is the nature of heteroskedasticity? What are its consequences if we have heteroskedasticity in our model? Third one, how to detect heteroskedasticity, and last one, we have to remedy if there is a heteroskedasticity. Okay, homoskedasticity is stated in the equation 1111. This means the variant from the beginning until the end observations is the same because there is no any sign here subscribed for the sigma square. Okay. It is different with the 1112 because there is I here in the sigma square. If there is I, this means the variance change from the first observations until the end of observations. Yes. This means the assumptions of one of assumptions of classical linear regression model is piloted if there is heteroskedasticity as stated in the equation 1112. Okay, this graph represents the homoskedasticity because the variant are the same from the first samples until the last sample. Okay. Different to another one here, the variant is smaller in the first sample and bigger until the last observation. This means in the graph 11.2 represent the heteroskedasticity, and in the upper one, this is 11.1, is homoskedasticity. Okay, there are various reasons why heteroskedasticity are found in our model. The first one, because of error learning models. Okay, for example, if in the beginning we are learning about the typing methods, of course we have more error compared to the experienced typewriter one. Okay, for example, we are learning how to drive a car. In the beginning, we have some accidents, but after we continued learning how to drive the car, the accident become smaller and smaller. This is a error learning models. And the second one is discontinuity income. For example, if we are just graduated from our university, our salary is very small, and then we work for certain time, we earn more money, then the money become higher, the income become higher. That means the income is different from the beginning until the, for example, after we work 10 years. This means here the income increasing as the time we work also increase. Okay. Then if we have a lot of money and then we buy house, if our house is big, this means we have to spend more money to finance our electricity bill, for example. But if we have a small house, no need to pay a big bill for electricity. And then we have here data collection method. For example, if you are collecting data for your thesis, in the first day, you have a little bit difficulty to get the sample. But after you practice, more practice, and you have to a lot of experience, so you can get easier how to interview the respondent. So by this technique, there is an improvement if we have experience. So we do not need long time to get more samples. The fourth one is outliers. It is common in the data. For example, if we have income, we have our sample, for example, yes, our respondent. Okay, the average income of our samples around 3 million. Okay, for example. But some of respondents have a huge income. So the huge income the respondent who have the respondent outlier. This is the problem of outlier. Okay, it is common in the data. Yeah, outliers also can produce this heteroskedasticity. If our samples are primary data, if we have primary data, we can drop the outliers to avoid heteroskedasticity. However, in the secondary data, we cannot drop the data. Okay, this is the difference between the primary data and secondary data. If you have primary data and you have a lot of sample size, you can drop the outliers sample. Okay. Another problem that causes heteroskedasticity coming from misspecification. Okay, for example, this specification here. For example, if our data are non-linear, then we estimate the linear model. So we have the heteroscedasticity problem. Okay, so it is better to correct model should be linear model. Okay, this is the problem of the heteroscedasticity caused by the misspecification. Okay, this is outlier. Okay, because this our average here around here, but we have here one outlier. This outlier can cause heteroscedasticity. Okay, the sixth one is skewness. The distributions of data are not normally distributed. So there is a possibility that our data will cause heteroscedasticity. For example, this, our data are concentrated on the right hand side or on the left hand side. Because of this, then the heteroscedasticity cannot be avoided. Okay, the seventh, the heteroscedasticity can also caused by incorrect data transformations. For example, if we have to make ratio, okay, ratio the difference transformations. Okay, for example, here, if we have, for example, this is nominal money demand. Okay. Our model for nominal money demand is a function of income, interest rate, and price. Yeah. So this model can be transformed into real money demand. Okay, real money demand. This means we have MD over P is equal to functions of real income. This means Y over P. This means we have real interest rate and without prices. Okay. Here is real interest rate. Real interest rate is nominal interest rate as by inflation rate. Okay, this is the model of real money demand. Okay, if we estimate in this real model, this means we have transformed model. This is transformed money demand model. This is nominal. Okay, this is transform money demand is real money demand. is common in our model. Also, we can also estimate, for example, if our data transform into per capita. For example, here we have consumptions. This is a consumption model. It's a function of Y here, income, and also interest rate. But here we have overpopulations. It's equal to functions of Y overpopulations and interest rate. Okay. But we cannot divide it, the interest rate with the populations. Okay. Only consumption per population, we get consumption per capita. Income of a population, we get income per capita. Okay. Okay, some of data also transformed into was different. I mean, this is was different in terms of was different. This is was different. It means if we have data here, okay, for example, we have here 1990, 1991, 1992. Okay, here, for example, here, we have, for example, here, X here, variables, X variables. We have 10 here, 16, 21. So we have here delta X. This means here no sample here because we have no previous data. Here this means 16 minus 10. This means here 6. Okay, here we have 21 minus 16. Okay, 5 here. Okay, this is transformation data. We transform data into first difference. And also because of here incorrect functional form, I explained already for you. For example, if we have linear data and we estimate in non-linear data, also can cause the heteroskedasticity. I explained before. Okay. Okay. If our data represent linear one, so don't estimate in linear model. Okay. If we have linear data, so don't estimate in the non-linear data model. Okay. Vice versa, if we have our data non-linear distributions, so it is better to estimate in non-linear model. This to avoid the problem of heteroskedasticity. Okay. Okay. If we have heteroskedasticity, what are the consequences to our estimated value? Okay. If we have heteroskedasticity, that means our residual will be bigger, then we have a bigger standard error. But we have bigger variance. If we have bigger variance, that means our model become not efficient. Okay? This is blue. Blue. I explain for you best linear unbiased estimator. Okay. In the presence of heteroscedasticity, so we have non-efficient okay, so it is still linear unbiased, but it is not efficient. Why the OLS estimator for beta 2 in equation 11.2.1 not best, although it is still unbiased, because we have bigger variance, so we have bigger standard error. If we have bigger variance, that means our model is not efficient compared to homoskedastic parameters. Okay. So what of model can be applied to estimate the presence of heteroskedasticity is actually I don't like to use GLS because GLS commonly used for okay. I prefer to use WLS. Okay, this is weighted least square. Okay. It is more appropriate in terms of heteroskedasticity. We have GLS, generalized this square. Okay, this one for serial correlations. This is, I prefer to use WLS for heteroskedasticity and GLS for serial correlations. We are talking this one next week. So, okay. Even though the almost the same, but it's different. Okay, how to estimate GLS? Okay, there are some problem in the heteroskedasticity. For example, if heteroskedasticity is caused by variance sigma square, as stated in the equation 11, this one, sigma square, this variant heteroskedasticity variance. So we divided all data with standard error of the equations. So we get equation 11.33. This one become y star here, y asterisk here. Y asterisk is a y of sigma. Okay. Also we divided x by sigma, and other x also we divided by sigma. So we have equation 11.34. It is weighted this square. Okay. Okay. Yeah. First, if we have the heteroskedasticity square. Then, okay, all variables are transformed into y over sigma x. For example, we have x2 here over sigma x3 over sigma. This is the first way of to solve our heteroscedasticity. Okay, we hope after transforming this variable into weighted, so we call this a weighted. We call this weighted. Okay, yeah, yeah. Y over sigma x2 over sigma and x3 over sigma are weighted. So why we call it weighted square? Okay, here weighted square. It means we still apply least square method. But we use weighted variables. Okay, after transforming the data into weighted variables, so here we hope our variant become 1. If we have a variant is 1, it means we have constant variant. Constant variant has been homoscedasticity. After transforming the data into weighted square, so we have equation 11.35 here. Sigma square become 1 here. So the problem of heteroscedasticity solved. Yeah. Weighted square, I explained for you already this one, weighted square. It's better to use this nomenclature for our model is weighted square, WNS, not generalized this square. Okay, consequences of heteroscedasticity on our model. Okay, actually, if there is heteroscedasticity, is if heteroscedasticity since in our model, so the estimated parameters are unbiased, linear, but not efficient, best, or So the problem of heteroskedasticity actually a problem about the efficiency of the estimated parameters. Okay, still unbiased. The important thing is unbiasedness. Still goal in this model. How to detect heteroskedasticity? Okay, we have some methods to detect heteroskedasticity. Okay, we know that heteroskedasticity related to the distributions of the variance. If variance distributed same from the samples, from the beginning of the sample until the last sample, so there is no heteroskedasticity, or our model is homoskedasticity. Okay, the first method is graphical methods. Okay, but this one is not so easy to detect whether the heteroskedasticity presents in our model or not. Yeah. Okay, this is a residual square. So we run the data, we get the residuals. So we make the graph here between residuals and y squared, y head. Okay, if the graph here, okay, same from the beginning until the end, this means homoskedastic variance. Okay? Here heteroskedastic variant, here homoskedastic variant. This is a method, the first method. We can use the graphical method. Okay, this is yeah, first approach graphical method. Okay, we have formal method. Okay, formal method is back test. This one back test. This we call it the one is informal method. Formal method. One is is let's so only some of them are Goldfeld contest. Contest. Bruce Pagan test. Pagan Godfrey. Pagan Godfrey test. White test. Okay, some of them here. We start with the park test. Okay. Park test. Yeah. It is assumed that the variant become bigger or smaller compared to the beginning observations. Okay, how to estimate this one? We can use, first we run the data, we get the residuals, we square the residuals, then we use this square residual, and then we transform the residual, square residual into log term, and then we run with the dependent variables. Okay. If beta statistically significant, is indicate that there is a heteroskedasticity. Pleasure test is almost the same to park test. Okay. The difference is in the park test, we transform the square residuals into log term. And here we take the absolute value of the residuals. So this means here negative become positive. Also, if the beta 2 here is significant, then there is a heteroskedasticity. Okay, we skip the Sparman ring test. We go to the Goldfeld test. Okay. Goldfeld test. This method is applicable to one assumed heteroskedasticity. Okay. Here, if this variance caused by the one of the variables, yeah, this assumed is 2. Okay, if this is 0, assumptions 11, 5, then postulate that sigma square I is proportional to square x variables. So how to use the Goldfeld test? First, okay, here Goldfeld test. Okay, for the Goldfeld test. Okay. First, we have to divide our data into 3 parts. Okay, here. For example, if we have 100 samples, so we have to run 2 parts. Okay, for example, 100 samples. We divide it by here. The first part here, for example, we have 40 here, 40 samples. The second, there is a middle part. We have 20 samples here. And the last one, the third part, we have 40 samples. So the important thing is first part must be the same the third part. Okay, must be the same. Okay. And then we have we have the first estimated, and we have the third estimated. Okay. The middle part is not estimated. We avoid the middle part. Okay, then common central observations here, I explained already. We have two estimated equation here, the first part and the third part. Okay, and then we calculate this lambda. Lambda comes from residual sum of square of the third part and the residual sum of square of the first part. We divide it by degree of freedom of each equation. Okay, the null hypothesis. Okay, here I have to explain for you in the heteroskedasticity. Null hypothesis for heteroskedasticity is homoskedasticity. Alternative hypothesis is heteroskedasticity. Okay. If H naught is rejected, it means there is okay, here. Okay, lambda here is F distributions. This one, the example for the ball field contest. Okay, Spartan good trade test. Okay, the success of golf field contest depend not only the value of central part of the samples, but also on the identifications of the correct X variable that cause the heteroskedasticity. Most data that have potential problem for heteroskedasticity, such as populations, GDP, okay, money supply, export, and etc. This is this data, okay, all of this kind of data have potential great heteroskedasticity. Some of them I okay. The difficulty is to find the correct X that has the, the, the potential to cause the heteroskedasticity. Okay. Okay, this limitation can be solved by using Bruce-Pagan-Godfrey test. Okay. Here is quite easy here. We estimate the data and then we have the residuals. Then we square the residuals. We use the square residual as dependent variable. Then we estimate the sigma square from the beginning estimation model with all the variables here in the model. So here the null hypothesis, if alpha 2 until alpha m is equal to 0, this means we have the alpha 1. Alpha 1 is a constant. If we have alpha 1, this means the model has a homoskedastic equation model. Otherwise, if we reject the null hypothesis, this means we have heteroskedasticity problem in our model. Okay. This one, how to estimate this one? Okay, first we estimate the OLS, and then we get residuals. And residuals, here we square residuals. We square residuals, we divide it by n, we have residual tilde residual, tilde sigma square. We use this tilde sigma square. Okay, we estimate this one. Pi is a sigma square of sigma tilde square. Okay, we regress Pi with all the variables, and then we calculate this statistic with the chi-square distributions. If S0 is rejected, this means we have heteroskedasticity. Otherwise, we have homoskedasticity. White test is a more simple one, okay, compared to other one. Here, we estimated the equations. We take the residuals, we square residuals, and then we include all the beginning variables from here, 11, 5, 21 here. We include this one, x2, x3 here, from these equations, and then we square it, become x2 square, x3 square, and then we multiply x2 with x3. If we have here 4 variables, for example, we have here x2 square, x3 square, x4 square, and then x2 times x3, x2 times x4, and x3 times x4. Okay? And then we calculate the NR square. This is also, the statistic has chi-square distribution data. Okay, if null hypothesis is rejected, this means we have the problem of heteroskedasticity. Okay. How to remedy the heteroskedasticity? I explained already this one, this model. We have this one. In the beginning of this class. Okay. Okay, this first, if we assume that the variance is proportional to the xi square, then we divided all the variables with the x, because it's one xi square, so we divided by x. Okay, this is transform data. We call it also weighted data. After transforming the data, we hope we will have this one, sigma square. That's mean homoskedastic model. Okay, this one. If x is the variant is proportional to xi square first. Okay. Second one, if the error variance is proportional to x, then we divided all variables with the square root of the x variables. Okay. If x square, we divide it by x. If proportional to x, we divide it by square root of x. And if we have this one, we have the expected value of y. That means this one is we divide it by the expected value of y. This mean of the equations. Okay. Yeah, we have we divide it by predicted value of y variable. Okay, and then we can transform our data into log term. Okay. You have any question here? No, any question? Okay, if you don't have any questions, I want to we have this one, can divide it, can share for you this data.
Yes, I have a question.
Okay, go on.
In solving heteroskedasticity, you in equation 11.3 and 11.4, you said if sigma square is equals to 1, you said it's assumed to be constant. So what if it's less than 1 or greater than 1? What kind of assumption should we have? Is it, we say it's constant or what?
11.3.
Yes, sir. 11.3 and 11.4.
Okay, let me see. This one you mean? This equation?
Yeah,
right?
yeah.
Okay. Here, after transforming the data into weighted square, so we hope we get the constant variant. Okay, because we divided all the data into weighted variables here, 11.3.6 here. This is transform data, this one. So we hope we can get the homoskedastic model, homoskedastic variance. If we have a homoskedastic variant, this means we have we fulfill of the assumption of the classical linear regression model. That means you mean?
I think it's 11.33. I think
11.
because yeah,
11.3.
Yeah, 3.
11.3 is one. Which one? 11.31?
Yeah, exactly. No, the 11.33. 3.
Oh, this one.
Yes, this one. Yeah,
okay.
Down. Yeah.
Why?
You said when solving for heteroskedasticity,
Yeah.
If sigma square end up to be 1, then we assume it as constant, as a
Yeah.
constant.
Yeah.
Now my question is, what if it's less than 1? Yeah, exactly. If it's less than 1. So what will be the assumption? Should we
Oh,
consider
you
it
mean
to be a constant?
okay? No, we have one only. Okay, in the beginning of our class, okay, maybe you forget it. Okay, we have the assumption of normality. Okay, the residual are normally distributed with zero mean and constant variance. Okay, constant variance. Okay, here if we write down in mathematical term, okay, distribution. I cannot write down here distribution for distribution is 0, 0 and 1. That's why we have this constant variance. 0 represent the mean, 1 represent the variance. You get it?
Yes, sir. Yes, sir. I
Okay.
get it.
Next, we can estimate here. Okay. Here. Can you see these FUs?
Yes, sir. But it's still blank.
Yeah, there is nothing on
Huh?
it. Yeah, we can
There's
see the
nothing on
eviews,
it. I mean, there's
but
reviews,
nothing.
but there's blank.
Okay. Now you can see it?
Yes, sir.
Can you see? Okay. We have this data. Okay. Now we want to estimate, for example, we have here some variables here. Okay, for example, we have money demand, M1. Okay, it's a function of income, GDP here, and interest rate, R rate, and also price level, inflation. Okay, we have 4 variables. Okay, we estimate here by OLS, this square method. Okay, so we have OLS. Okay, in theory, it is stated that if income increase, the demand for money also increase. That's been positive relationship between income and money demand. Here we have the positive equation here, estimated parameters, and it is significant. But here, inflation should be positive. That means if price increase, the demand for money also increase, because we need more money to fulfill our expenses because the price has increased. Right here we have negative but not significant. Okay, this is one kind of problem. Okay, for example, if we residual series here. Residual series. We have here, for example, error 1. We got the error 1. This one residuals. Okay. And we okay, we have to calculate heteroskedasticity. This one heteroskedasticity. This is a simple one. Okay, for example, we have this Bruce Pagan. Now we have null hypothesis here. Null hypothesis is homoskedasticity. Okay. The alternative hypothesis is heteroskedasticity. Okay. So here we have statistics 7 point something here, 9 something. The probability value is 0.00. This means we reject null hypothesis. This means there is heteroskedasticity in our model. Okay, this one Bush Pagan. Also, we can test for other tests. RV, RV also produce the same thing, heteroskedasticity in our model, because all of this probability value less than 0.05. We can also test with the glaciers. Yeah, also we have heteroscedasticity. And then if we have here arch, same, we have heteroscedasticity. If, for example, we test here with Y test, okay, also we have heteroscedasticity. This means we have this problem of heteroscedasticity. If you have here whited, okay, you have variance here. For example, we use these options to solve a problem. But here we have the same thing. There is no difference between the previous model. Okay, for example, we change the option become standard deviations. Okay, you can use here average. Okay, same. Okay, we have in first standard deviations. Simple here. Suppose we have. Okay, this one we divided by GDP. We have here GDP as a potential to create heteroscedasticity. Our model become more appropriate. Here, you see here, GDP still positive and significant. Interest rate still, it is theoretically significant because it has a negative sign here, but a little bit not significant. This around 10% here. But now inflations become positive and significant. Okay, we have this one weighted square in our model. We can also, for example, we choose here inverse of standard deviations. Now it's not appropriate model here. Inverse variant. Not significant for the interest rate, even 5%, 10%. Okay. Standard deviations. We get the previous one there. Okay, which is better than the other model. Okay, if we estimate by variance. Okay, variant is not as good as this one. So the best one is the standard deviations. Okay. Yes, we have more appropriate one. Okay. Now if we change the model, become linear one, log linear one. This one we change to the log LGDP, but interest rate, because the interest rate in terms of percentage, we cannot check it to inflation is in percentage also. So we have now two variables in terms of log term, two variables already in terms of percentage. This one, our model here, we have GDP positive, significant, interest rate negative, significant, but inflation is negative, not significant. So if we apply again this our model, but it is not so smooth to estimate this one. Oh, sorry, we have problem in the estimations. Can you see these FVs?
Yes, sir.
Okay, now we estimate again. Okay, now we estimate in terms of log term, GDP, okay, interest rate, and inflation rate. Okay. And we estimate in terms of OLS. Okay, here is negative but not significant. Here negative significant is contrary to the theory. Now we use this in terms of WLS within the square. Okay. With the waging variable is log of GDP. Here we have the GDP is significant, negative significant, interest rates negative but not significant. This inflation is still negative but not significant. So we change the option into inverse variant. Now we almost the same. Okay. First we change again into standard deviation model, like the previous one. Now this negative significant is the worst one. Okay. Now, if we estimate in the, okay, it's not good. Okay, that's mean the best model is one is in terms of nominal. This one. Okay. And the option is weighted here. And here standard deviations. And the previous one is a best model in our estimated demand for money. Okay. Any other questions?
Yeah, sir.
Yeah.
In this model, like for inflation, if it is negative and significant at the same time, that negative, what does it imply?
Yeah. Which one?
Inflation.
Inflation here. Inflation is positive significant. Okay.
Yeah,
This
I mean,
one.
if it is negative, like the previous option.
Oh yeah, I see. If you have negative insignificant, that means you have problem here. Okay, for example. Okay, for example, I want to show you. Yeah. Okay, for example, we have money. Okay, we have money here, 1 million rupiah. Okay, 1 million. And then we buy rice, for example. Yeah, 250,000. Okay. Yes. Other expenses. Okay. For example, we have 750. Okay, and then price of rice increase. Okay, from 250,000 became 300,000, for example. So now you have limited. Okay? We only have this means we only have 700,000 for other expenses. Okay. If we want to achieve our previous expenditures, this means we need more money, but 50,000, right? This is theoretically stated that if the price increase, this means if the price increase, this means we need more money to buy the same thing before the increase price. But if we have here negative coefficient, this means okay, the increase in price, then the demand for money also decrease. It's impossible. You get the point?
Yeah. Thank you.
If price increase, that means we need more money. This is theoretically. That means the price and demand for money has positive relationship. Okay?
Yes, sir. Yeah.
Okay. If you say that the increase in the price, then you do not need more money. It's not. It is impossible to pay everything in the higher price level. Okay. Okay. Any other questions? Okay. No other question?